The next major topic I want to discuss is the hardware and devices used for accessing a network. The first device to look at is the NIC. NIC stands for Network Interface Card or Network Interface Controller. Network Interface Card is a little bit older term because back when this term was first used, almost all the network interface devices that you put into a computer came in the form of an expansion card. However, nowadays, your network interface is generally built into the motherboard or directly into the device. Because of this, we've begun to use the term Network Interface Controller to refer to the NIC. What the NIC does is it allows a computer or other device to gain access to the hardware of a network. The NIC that does this, or the device that does this, can come in the form of the aforementioned expansion card. It can also be built directly into the motherboard, and even more recently, the device that gives a computer access to the hardware can even come in the form of a USB device. Either way, whatever form it comes into is still referred to as the NIC. The NIC works on layers 1 and 2 of the OSI model. When you're purchasing a NIC, you need to make sure that the NIC matches up to the technology that's being used. There's several different considerations to keep in mind when you do this. First, you need to make sure that the media technology matches up to the NIC you're using. For example, if I'm using an 802.11n Wi-Fi network, the NIC I use to gain access to that network also has to be able to support the 802.11 standard. In the same way, if I'm using unshielded twisted pair to connect up my network, I need to make sure that the NIC I put in the computer to do that is also able to use the unshielded twisted pair. Speed is another consideration when you're purchasing or choosing a NIC to use on your network. If I have a gigabit Ethernet network running, I need to make sure that the NIC that I use to gain access to that network is also capable of using the gigabit Ethernet standard. A final consideration is I need to make sure that the NIC I use matches the network architecture being used. For example, if I'm using a token ring architecture on my network, the NIC I use to gain access to that network needs to also follow the token ring architecture. In the same way, if I'm using Ethernet as my network architecture, the NIC I use has to be able to interface and use the Ethernet architecture. The next type of device I'd like to talk about are hubs. Hubs are an older technology that you won't see too much of anymore, and that's because hubs are basically falling out of favor in preference to the more modern switches. The hub actually worked on layer 1 of the OSI model. Also, logically, the hubs functioned as a bus. What that means is a signal that came into a hub would then be broadcasted to all the other devices connected to the hub, thereby generating a bus topology. This meant, of course, that the computers connected to the hub had to use contention to find out who could send their data on the network first. If you had too many hosts on a single hub, you could actually have too many collisions taking place. And if you had too many hosts, it could eventually get to the point where the collisions would actually bring down the entire network. There were 3 main types of hubs. There were the passive hubs, active hubs, and finally, intelligent hubs. The passive hubs worked a lot like a cable splitter. Basically what that means is that when a signal came in and was splitted out, the more devices connected to the passive hub, the weaker the signal got for each device. The reason the signal got weaker for each device is because depending on how many devices you had to divide the power of the signal that many times so that each device could receive the signal. Active hubs were an improvement over the passive hubs because the active hubs needed a power source. The reason the active hubs needed a power source is because they added power to a signal when it passed through a port. In this way, active hubs were able to prevent the weakening of a signal by having multiple devices connected to it. Active hubs, just like passive hubs, did, however, repeat the signal to all the other devices connected to the hub, thus creating a bus environment again with the inherent weaknesses of a bus environment. Aside from connecting devices to the network, the active hub could also be used to connect other active hubs together. However, when we connected multiple active hubs together, we had to make sure that we followed the 5-4-3 rule. The 5-4-3 rule basically says this. 1, you can have no more than 5 segments total on your network. 2, you can only have up to 4 devices or active hubs linking the network together. And 3, only 3 of your 5 segments were allowed to be populated by computers. This diagram helps illustrate that. As you can see, when you count the computers on either end of the network, you have a total of 5 different segments. Those 5 segments are in turn connected together by 4 different active hubs, but only 3 of those segments are able to have computers connected to them. Thus, this illustration shows what a 5-4-3 rule would look like in practice. Beyond active hubs, we had intelligent hubs. Intelligent hubs were basically active hubs with additional features added to them. One of the most common features to put on an intelligent hub was the ability to run network diagnostics. A hub that had the ability to run network diagnostics was able to troubleshoot the network and send back a report of any problems that were on the network. That report could then be used to go in and fix the problem. The intelligent hub could also sometimes use that report to route around problems it found on the network. Another feature added, or another ability added to intelligent hubs, was the ability to manage their own ports, or a management ability. Intelligent hubs that had the management ability had the ability to turn on and turn off ports as needed to more efficiently manage the devices connected to that hub. There were a few other abilities that were added to intelligent hubs, but they weren't nearly as common or as widely used as the 2 we just mentioned. The next device I want to look at is a device called a bridge. Bridges were used to take a large network and break it into smaller segments. If you remember previously, I told you if you put too many computers on a segment, then those computers would begin creating so many collisions that you couldn't send data through the segment. Well, bridges were a device intended to minimize that or put a stop to it. The way the bridge would do that is you would take the large segment with a lot of devices, you place the bridge in the middle of that segment, thereby effectively creating 2 smaller segments with half the number of computers on them. The result would be fewer collisions and better ability to get the packets through the network communications link. Bridges are an older technology, but they are relevant to talk about because the bridges are the forerunner to the modern switches that we use today. The bridge, just like the switch, works on the layer 2 of the OSI model. What makes the bridge have the ability to separate a segment into 2 smaller segments is the fact that the bridge can read the frames that come into it, and by looking at the address in the frame, it can determine whether a frame is allowed to pass through the segment or should be blocked because it's coming from a location that already has that address on it. In this way, bridges are able to reduce the amount of traffic on a network by dividing it up into multiple segments. The next type of networking device I would like to talk about are switches. Switches are devices that are used to connect multiple computers together. Switches also, like bridges, primarily work on layer 2 of the OSI model. However, there are some switches that can work on layers above layer 2 as well as layer 2. In the event that a switch is able to work on more than one layer of the OSI model, it is called a multi-layer switch. The basic switch is the most common type of switch you'll see out in the real world. A basic switch is essentially a multi-port bridge. What that means is the switch can be used to take a much larger network and separate it into smaller networks or smaller segments called collision domains. The way the switch sets up these collision domains is it takes 2 devices that want to talk to each other and links only the 2 ports that are relevant to each other so the 2 devices can effectively have a point-to-point communication between each other. This results in a collision domain of only two machines. And since only two machines are involved in the collision domain, and both machine has a send and receive pair of wires, the result is you don't have any collisions on your network. Another advantage of setting up the point-to-point connection between two devices and letting them talk is that it enables the basic switch to set up a communication between the two ports at full speed. Without this point-to-point communication, the switch would have to divide the signal coming in by the number of ports it has on it, much like a hub would. But by setting up the point-to-point connections, or setting up multiple point-to-point connections as different devices want to talk to each other, the basic switch avoids the necessity of dividing up its bandwidth, thus allowing the ports to communicate at full speed. This also has the added advantage if computers are connecting to each other and talking to each other directly in a point-to-point type configuration, then it makes it much more difficult for somebody to listen in to the traffic of the network and hear everything that's going on in it. Beyond using basic switches to divide up the network and to set up point-to-point connections, basic switches can also commonly be used to convert media from one type to another. A very common configuration you'll find in a basic switch, especially those used in a corporate environment, is that you'll find fiber coming into the switch, but the ports going out of the switch and connecting up various devices to the switch use copper twisted pair ports. This effectively creates a switch that has fiber coming in and copper going out, thereby converting the media from a fiber optic to a copper twisted pair. Managed switch and unmanaged switches are two variations on the basic switch. Managed switches are switches that are programmable. The reason you would program a switch is because by programming the switch, you can control how data behaves on your network. This type of programmable basic switch, or managed switch as it's called, is the most common switch you'll find in a corporate environment. Unmanaged switches, on the other hand, are not fully programmable. Instead, they come with a default configuration. While many unmanaged switches will allow you to change the default configuration, they only allow the changes to take place in a predefined, limited way. Outside of the predefined, limited changes that are allowed in the default configuration, you really can't change the programming of an unmanaged switch. In fact, some unmanaged switches go to the extreme that you can't change your configuration at all. Basically, whatever configuration comes on the unmanaged switch, that's the configuration you're stuck with. Most home networks or small office home office networks will use the unmanaged style basic switch to set up their networks. The next networking device I'd like to talk about is routers. Routers are used to move data around large networks such as WANs. Primarily, a router is going to work on layer 3 and layer 4 of the OSI model, though some routers can actually use higher layers as well. Routers are also intelligent devices. Routers have to be intelligent because they need to be able to make independent decisions about sending data around the network. When making decisions about sending data around a network, there are a number of criteria that routers can use to do this. One such criteria is hops. Hops refer to the number of nodes a packet has to pass through in order to get to its destination. The router will count the hops available by different routes, and it'll choose the route with the smallest number of hops necessary to get to the destination it is trying to send the packet to. Routers can also use network traffic as a criteria for determining the best route. In this situation, the router looks at how much traffic is on the network and which routes on the network have more traffic over those routers that have less traffic. And if it's appropriate, the router will choose routes that have less traffic in order to speed up the data getting to the destination it is intended for. Beyond traffic, a router can also use throughput as a way to determine the best route. Throughput refers to how fast data can move through a particular connection, or another way of saying that is throughput is the amount of data that can pass through a link in a specific amount of time. Routers will look at the throughput of various routes to different destinations, and they'll see the route that takes the least time to send the data through, and they'll choose that route as opposed to a route that has slower throughput. Another criteria routers can use is network reliability. In other words, the router is able to keep track of how reliable different routes are on the network. By keeping a long-term log of the reliability of different routes, the router is able to choose the route that has the most reliability. Reliability referring, of course, to the route that's most likely to not be down or most likely to get the data where it needs to get sent to. Routers will use all this information that they gather as well as other information determined by the routing protocols they use, and they'll create tables that help them generate a set of paths to send the data to all the destinations they're connected to. Routers will also use this information to keep the tables up to date, because just because a certain route is the best route now doesn't mean something can't happen to that route later, which makes it a poorer choice. And so using this information that the router is constantly gathering, it can keep its routing tables up to date as well. Routers are also programmable just like switches are. Some of the things you can program into routers is their interface configuration. Another thing you can program into routers is you can tell them which networks they're connected to. You can also use programming to define for the router what type of information or what type of packet is allowed through a router and what type of packet is not allowed through a router. Finally, you can also program multiple protocols into a router, thereby making the router more flexible. The final networking device I'd like to talk about are access points. Access points are devices that allow computers to gain access to a larger network. Commonly, access points are used in home environments so that all the computers in the house can gain access to the internet through the router or whatever that was provided by the internet service provider that the home uses. Such access points can either be wired or wireless, though by far the wireless access point is the most common access point you're going to run across, both in the home and the small office, home office environment, and even out in the larger corporate environment. Wireless access is by far the most likely you'll see. When referring to wireless access points, we often use the term WAP to shorten it so that we don't have to say the whole wireless access point. Wireless access points are commonly used to give public access to the internet in many locations. Such locations where wireless access points are used to give public access to the internet would be locations like libraries, restaurants, airports, hotels, and many other similar locations. While wireless access points can be used to give a person access to the internet in a public location, wireless access points can also be used as a connectivity device. When used as a connectivity device, what the wireless access point does is it is used by a corporation to give their end users access to the corporate network. That may or may not result in also giving them access to the internet. When wireless access points are used as connectivity devices, they generally have several features built into them. Some of the features that have built into them for this purpose are things like authentication and the ability to encrypt the signals that are sent both to and from the wireless access point. Also, WAPs used in this capacity will generally combine the role of both a router and a switch, and like routers and switches, they can be programmed to a limited extent.